auxiliary flank, this part of the auxiliary cutting edge is engaged in cutting. So, you have also rubbing action over this auxiliary flank, and as a result of that we may expect that here you have rubbing action and you have rubbing mark. So, wear will take place something like this, and wear may also take place like this on this side. So, this will be the wear on the auxiliary side, you have a wear on the principal side. So, this is the wear on the cutting tool, and in addition to that you can imagine the chip is flowing like this. This is the direction of chip flow, and as a result of this you have also rubbing contact between the chip and the tool surface, and there it is a impression left, and it is in the form of a cavity, and this cavity is like this. So, you can see this is like a cavity which forms on the rake face, and this is called the crater wear. That means, the wear on the rake surface, that is in the form of a cavity crater, that is why we call it crater, and these are actually flat. It is flat surface on this side, it is also one flat surface on the auxiliary side, and both surfaces are flat, and you can look into that those surfaces should be parallel to what? Parallel to the tangential plane or cutting plane. So, obviously, here the clearance will be 0. So, this clearance 0 means tool is not efficient there with 0 clearance, it will promote severe rubbing. So, that is why that growth of this wear, that means it will keep on growing down the flank, and at certain point the rubbing will be so much, it leads to noise, vibration, increase of cutting force, and that will not only spoil the job workpiece here, particularly this side, because this side it is a transient surface, we need not pay any attention on this side. However, on this side, that means where we have the triangle formation, it is participation of both sides. If you have this damage on this surface because of this wear on this tool, then your roughness will be more than that what we can predict by this theoretical formulation. So, this side will be called the flank wear on the principal flank, and this side we call the flank wear for the auxiliary side, and this happens to be the crater. Now, friend, this is a quantitative understanding, it is a qualitative understanding, but we cannot say low wear volume, high wear volume, there must be some quantification. Yes, after that we must declare the tool unfit and we must withdraw the cutting tool. So, there must be a quantification, and for that ISO has certain recommendation. ISO means International Standard Organization, they have certain recommendation, and one has to follow those recommendation to define the life of the tool for a particular operation. So, just an extension, let me draw a larger one, so that will give you some insight into that. It is just not a flank or crater wear, it is something more than that. So, let me quickly conclude that part. So, let us draw this picture once more. Okay. So, on the side I draw this one also, location of this cutting tool like this, and then we show here the workpiece. So, this is the portion of the cutting edge engaged in cutting, and what we find here, that as we have seen that if we draw one line, say the location before 1 RPM. So, it was after 1 rpm and it is a beginning of the cut. So, here you have another instant. So, what I mean to say, you have this border line, this point is located at the border, and beyond that there is no material. Similarly, here we have one border. So, what is the significance of this border? Actually, this point is very sharp, it is strain hardened. So, this point virtually acts like a cutting tool on the original cutting tool. So, I have already shown you that this is the flank wear, this is the flank wear and that is the border, but here what we find? We find a V notch, it is almost a cutting knife. So, it is almost a cutting knife. So, with that we have a notch formation, and where does this notch form? It is one is in the border line of the depth of cut, this is one, and this is another where this your interaction of the auxiliary cutting edge and the main cutting edge, and they are crossing this point where they are crossing, they are intersecting. So, these are the 2 points, after that there is no material. So, at this point you have 2 sharp points which virtually act like 2 knives, and as a result of that you have like a V notch, notch formation. Notch has certain width and certain groove, and in between you have this kind of this location of this crater. So, this is crater, and it is interesting, the chip flows like this, chip is flowing like this. So, it is the chip is sliding. So, there is a sliding mark, that means as the chip flows, chip is following this line, these are the 2 lines. So, 2 edges of the chip, please look what I am trying to locate, this is one edge of the chip, that is another edge of the chip. These 2 edges can be characterized by their number 1, they are hard, they are hot and they are sharp. These 2 edges are 3 qualification adjective, hard, hot and sharp. They are also acting like 2 knives. So, along this you can also have this sliding mark, and these are called sliding wear. So, friend, please note down, on the rake surface you have the crater formation, plus along the 2 edges of the chip in the direction of chip flow you have the sliding mark, and it will end here because the lifting of the chip, it gets separated, and if you continue down the flank you get the location of the notch. So, this side it is the rubbing action of the workpiece, and there you have the notch formation because of the sharp point on the uncut material, and this is the finished material, this is the transient surface, this is the edge of the original uncut material, raw material, this is the finished surface, and this is the transient surface. So, this point means here this point, along the rake you have sliding wear mark, along this side auxiliary side you have one more sliding wear mark, and down the auxiliary you have flank you have the V notch of auxiliary flank. Here you have the groove, that means the knife starts cutting, and this is the notch on the principal flank. So, friend, finally let me tell you this one is the flank wear on the principal flank, this side is the flank wear on the auxiliary side, and on the principal flank you have a notch at the border line. Similarly, you have another notch on the border line on the auxiliary side, you have the sliding mark, these are part of the tool wear. Now, so this is also sliding wear, these are the 2 marks, and finally inside you have the crater volume. So, everything, all this feature that leads to removal of the tool material, and all are very damaging and alarming. Now, how to quantify all these things? So far we have discussed in detail flank wear pattern and crater wear pattern. Now we see, thank you. Okay. So, now friend, it is wear and temperature. This is very important and interesting in that this wear phenomena, it may be because of abrasion, as we see here, this is we call abrasive wear. Okay. So, friend, this is the baseline temperature and that is the wear volume. It is the weightage of different wear pattern, wear phenomena. Now, here it is adhesive wear, then you have in between it is abrasive wear. It is because of the hard material which is rubbing, and adhesive wear means material gets attached like weldment formation, and then the bond is broken because of the pull or the drag, and in the process if this bond is strong, it may so happen that a part of the tool may get torn and it will be carried away by the chip. It can be also happen on the flank side, but it is mostly on the at the chip tool interface because of the simple reason temperature is higher at that in that zone in comparison to the flank temperature, and you have tremendous amount of normal pressure. So, that means it is adhesive wear. But interesting thing is that as you increase the temperature or the temperature accelerates, it goes up, and this is because of velocity and feet mostly, that also we have noted. So, because of that hardness will fall, that is number 1, that may lead to abrasive wear because hardness is falling. Abrasive wear resistance means hardness. However, now comes one new mechanism. It is actually opening the floodgate. It has nothing to do with hardness of the material, though we have noted that temperature means fall of hardness, but it is just not the hardness. Now, the material of the tool is showing its resistance, its weakness against chemical attack. Abrasive wear means a mechanical attack, which because of the loss of hardness may be also aggravated, but here because of the rise of temperature, all this chemical reaction or mutual dissolution like a salt and solvent, that may also take place, and finally, there will be a transportation or movement of the material across the interface, and this is by the process of diffusion. So, this will open up the floodgate for chemical reaction, chemical dissolution by this diffusion. So, this is something one has to look into, and it is for one to decide upon the choice of the tool material, and it is in the high speed and dry machining. Okay. So, friend, nowadays we cannot just afford to use all those chemical additives and other things because of the strict condition imposed on the use of those which create pollution, and so that is why it is only high speed under dry condition or little cooling action that is permitted, and with that you must understand what would be the best tool material to combat that wear. This picture, this diagram is significant in that you understand the proportion of different wear mechanism compare in relation to the temperature. Now, what we find? So, failure of cutting tool, it is I have narrated failure of cutting tool at high cutting speed means high cutting temperature. It is reactivity or solubility. These two material tool work can react, and then there will be loss of tool material, or it may be that work material acts like a solvent and it dissolves the tool material. So, both are possible, and this is one thing one has to pay attention. So, friend, coming here, the consequence of flank wear on the tool. You can see here, just I have shown schematically that this was the original tool, and this is the direction of velocity, and there was the original clearance angle. Suppose in this case rake is 0, even rake is 0, no problem for us, we can accept this thing. So, what we find that this line what we have shown, that already we have shown just now by my hand sketching those rubbing marks down the flank. So, that is down the flank, and as a result of this tool tip is no more in existence. So, it is non-existent now, and you can see this area of the cross section into the width of the cut, means width of the chip. So, width of the chip or width of the cut into this radial loss, and it is the width of the flank that will give you the total volume of the material disappeared from the scene. So, this is the triangular area into the width of the cut in this direction that will give you that kind of volume material, and you can imagine that this is the width of the flank, and over this your clearance angle is 0. So, now you can you forget this part. So, your tool is only from this point down this flank, it is here. So, over this there is no clearance, and that will lead to increase of force, temperature, rubbing and so many things, and which will finally spoil your job. Why? Because surface of the flank is not smooth, force will be too much, temperature will be high, temperature is also damaging, residual stress, then dimensional deviation, oxidation, burning, lot of things are there, and when the force is high, it may lead to also vibration, deflection of the workpiece. It is held between the center, and I have already mentioned that Py component or the thrust component of the cutting force is so detrimental that ultimately depth of cut will be affected, and that means your accuracy, attaining that accuracy will become a difficult task assignment. So, naturally what is our objective here? Our objective here is to how to minimize this radial loss and how to minimize as a consequence of that this width of the flank wear, and for that you must have the best possible candidate as a tool material, so that your this just now what I have shown you this particular slide, this particular slide, that here you do not open the floodgate for diffusion or chemical reaction. So, this should be your best tool material, and it is under a particular cutting condition and the work material, that also comes very much in the picture. So, friend, here it is the summary. We have already mentioned accuracy will be impaired, surface roughness will be affected, it goes up, cutting force goes up, cutting temperature goes up. So, those are the few things one has to look into. So, one has to look into. So, finally, what we find? So, friend, here very interesting thing. So, we can measure the VB. So, what is VB? I have just now mentioned what is that VB, flank wear. So, this is the width of the flank wear, and you have to measure from this direction. So, friend, now we have to see this diagram. So, this diagram please. So, where is VB? VB is here. So, this width what I am showing with this arrow. So, that is the VB. So, this VB has to be restricted, and so this VB you can measure under the microscope. This value of VB, placing the tool by giving a quarter turn, this will face the your objective of the microscope, and you can clearly measure this wear pattern, the geometry. So, VC is measurable, there is as such no problem. Okay. So, this is where we are now. So, we have to get to this VB, and this VB just now I have mentioned that rate of growth, it is a general representation of any wear part which is submitted to this tribological application. So, friend, what I show you here, this is machining time 1 minute, 10 minutes, 40 minutes. You keep on measuring VB, and it is maybe an interval of 1 minute or 2 minutes depending upon the rate of growth. And finally, you have, as say it is 30 meter per minute for HSS, or say it is carbide tool, we start with 50 meter per minute, 100 meter per minute, 200 meter per minute and 300 meter per minute. And you see, this is our observation, this is just not a hypothetical one, and with increase of speed temperature also rises, and that actually leads to diffusion thermally sensitive wear, and because of that wear rate is so high. Now, with this we can find that this curve is shifting. So, here one scientist has to play the role to get the work material, so that you change now the tool material. This is on the tool material, you change the tool material in such a manner that you can again bring down the wear rate to this rate. So, that is the research achievement, or that is the fruit of the research. So, you have to look for those materials, and finally, you keep a value of VB, which is the ultimate limit for the tool to work. And if it is the limit in VB, means it is the dimension of length. So, we put it as 0.3 millimeter or 300 micron average flank wear. In that case, what we find that this gives you this lifetime. Here this is the lifetime, and here this is the lifetime, and the fourth case this is the lifetime. In summary, for VC1 lowest high cutting speed, this is the lifetime. For VC2 next higher, this is the lifetime. VC3 which is greater than VC2, this is the lifetime, and you see it is also falling exponentially. So, when with this what we can see here, that we have something to show, then this comes in the form of, as you put it here, as this values, that means VC1 TL1, VC2 TL2, VC3 TL3 means tool life, VC4 TL4. So, that is also not falling linearly, but exponentially. And finally, we find that in experimentally, when we collect those datas, then it comes to a form. This is one tool, say tool T1, and this is it is not giving very high performance, high performance. So, naturally we have to go for a better tool where we can change the slope of this curve and also the intercept. That means, here slope means n and this position means c. So, it is actually, we know Taylor's tool life equation, Vt to the power n is equal to constant. So, this is we call Taylor's tool life equation. And now comes the effect of tool geometry on tool life and clearance angle, effect of principal cutting edge angle. So, friend, this is, we understand that tool life, it is very much connected with your cutting temperature. So, it is obvious that when we have tool life, this is tool life and rake, it will be high somewhere here and then it will be falling. For tool life, it is also the same trend. When it is the clearance angle, this is like this, but when it is the angle phi, it is the tool life, it is falling. So, friend, everywhere indirectly what we have, okay, everywhere what we have indirectly, that this is actually connected to temperature. So, when we increase this gamma, then force, we bring down the force, and that brings down the temperature because of the less requirement of energy. But when we give further rake, then the mass of the tool available to bring down the temperature is less, and same argument we can advance also for the clearance angle. So, in one case you have less rubbing, less temperature, and when you increase the clearance beyond certain limit, because of the size of the tool and the mass involved on the tool is less, and that may lead to temperature. But when it is phi, you can imagine it is A1 means S sin phi, and also the length of the active section of the cutting edge, which keeps on changing for a given depth of cut, and this we have covered. If you see the lecture of the previous class, you can immediately come to that conclusion. So, for the same depth of cut, you can have larger width of cut, and larger width of cut means thermodynamic load per unit width of the cutting edge will be reduced, and this is very much connected with, that means higher the value of phi, that will lead to higher temperature and loss of life of the tool. Now, with this we can go. Now, friend, this is called a concept of chip equivalent. Now, significance of chip equivalent, I have shown what is mean by L. L means the total length of the cutting edge, which includes principal cutting edge and the auxiliary cutting edge. So, this we have just now discussed while considering the wear on the both principal cutting edge and the auxiliary cutting edge. So, it is the total length. So, total length divided by ST. What is ST? ST means cross sectional area of the chip. So, if I can keep L by ST, this ratio as constant, that is a very strategic way of controlling the temperature, then I can keep the cutting temperature also constant. So, if I like to increase the value of S to increase the material removal rate, then S means increase of temperature. So, in that proportion you have to increase the value of L without changing the depth of cut, just by changing the value of phi and phi 1 or the nose radius, and if you judiciously choose that one, and then this ratio what is known as chip equivalent, you can keep the cutting temperature constant and without any change in wear on the tool. And this one. So, friend, this is the periodic table, we can go straight. So, friend, it is interesting, though we have not touched much of that, but I like to draw your attention that all the cutting tool materials are selected from these transitional elements of 4B, 6B, 5B and 6B. It is titanium, zirconium, hafnium, vanadium, niobium, tantalum and chromium, molybdenum, tungsten. This is the metal side, cation side, and also aluminum, silicon also becomes strategic tool material, I mean the metal component. And what you have on the non-metal sides, boron, carbon, nitrogen and oxygen. It means you have titanium carbide, titanium nitride, titanium oxide. So, metal, non-metal makes one composition, and that becomes one of the refractory material which can give you that hardness or anti-welding property or very, very high chemical stability. So, from this with a right combination you can get a cutting tool which can give you that kind of leverage against the wear. Okay, friend, with that we have come to almost to conclusion. So, I have given these references, these are very useful book, one can look into those books, very well illustrated book, and you will feel like going through those books, reading those books and enrich your knowledge. And with that I go to some of these questions, and you can look into those questions, and if you have any clarification, maybe we can have an interaction. So, you go to question number 1, I need not read out, you can go through it. It is concerning tool life. Then you have concerning the tool life and the process parameter. In first case it is the geometry, and then it is the mechanism of the tool wear at high speed. Then in high speed machining, which one gives you the highest resistance? It means you have to look in which one gives the best chemical stability against iron. It need not to be diamond, and diamond in as a principle should not be used against steel because of the diffusion of carbon from diamond towards steel. It is very hard, but chemically very weak against steel. So, diamond is no for steel, it is good for aluminum or cast iron. And for machining aluminum, it is the other side, diamond is the best candidate and not TIN or TIC, because aluminum acts like a solvent for this solute. So, this thing will be literally eaten up by this aluminum during cutting. So, with that we conclude this session. We have mentioned that this tool life and this dependence of tool life directly on velocity, that is Taylor's tool life equation, what we have seen as V 2 to the power n is equal to constant, but it can be more generalized in this form that T is equal to some constant, obviously this value will change, and then we can put it in the form of this V to the power x. That means it is 1 upon n, it comes automatically. So, we put on the left hand side directly tool life. However, here to include the effect of S, that can be also observed, and it can be put as S to the power y and then depth of cut as T to the power z. Obviously, the idea is that the 3 parameters speed, feed, depth of cut, how they are going to influence the tool life, and these are all experimentally derived. You can imagine the effect of velocity on cutting temperature and effect of feed on temperature is more prominent than the effect of depth of cut. Depth of cut does not influence, because as we increase the depth of cut, force increases, and force means force into velocity energy, but thermodynamic load per unit length of the cutting edge, that remains same. That means the specific load does not change. So, that is why we see the depth of cut in that way does not affect the tool life or the cutting temperature. Rather, what we see that if we can increase the T by S ratio, that means compared to the feed, if we increase the depth of cut, in that case rather we can bring down the cutting temperature in a very positive way, and that has a favorable effect on this life of the tool. And rake clearance, that we have touched, but one thing should be mentioned here, that this figure we have 2 notch. So, this width of the notch we put as V n, here this is the width of the notch, that means this from this point to this point, what is the dimension. So, you put, just now I have mentioned, you put it under the microscope, put it against the eyepiece, and you see on the objective entire wear pattern, and you can measure the dimension at different position, and this is called V s. So, V n is the width of notch on the principal flank, V s is the width of notch at the auxiliary flank, and what is V b? V b is actually average flank wear. So, this is one cutting tool, top view, and here we have the crater. So, this is a tool with phi 90. Here we can put the workpiece. So, this is a cutting tool like this. Now, if I take the view on this side, I can draw it here or on this side, then what I find that this will be more or less the shape of the tool. That means, looking from this side, the view on the y plane or on the cutting plane, and if you take a section on this side, it is the orthogonal section, and if you take the tool here, what we reasonably see that it is the flank wear, that means this will be the flank wear, then you have the clearance, and then you have this cavity. So, this cavity means the cavity what I mean, and this is the flank wear. You see it from the cross sectional projection, because this would have been like this material is gone, it is disappeared, and here from the side you can see this as the flank wear, and here you have the notch. So, the same notch you can represent by this diagram, which we see in the isometric representation as V n. Same V n you can see like this, and this you can really measure, and V b means here the average of the flank wear over this zone, that we call the average flank wear, V b, average value of the flank wear. Now, when the wear is uniform all through, more or less uniform, you consider the average as V b, and put VB as 300 micron, that is your wear limit, and when this limit is reached, life of the tool has come to an end. Now, if this wear is not uniform, say it is not uniform, I draw one more figure. This gives you the clearance, and here you have the wear, and it comes like this, and then you have the V notch, and here it is not that uniform. So, in this case we cannot just make the average of this maximum and some minimum, but there we have to take also the maximum, and if it is so, then we call it V maximum, and if it is a non-uniform pattern, then we put V maximum for the wear criteria, and that we take as 500 micron. The whole idea here is to limit the life of the tool, and it is assumed that with this wear the tool operation is not favorable at all, and this time has come to withdraw the cutting tool, but this is a guideline given by ISO for this. Now, when it comes to the crater, so one thing we can see that this 0 clearance because of VB or Vmax, that affects what? It affects the PZ, because in this direction you have the PZ, PZ is in this direction, tool is forcing. Now, when you have 0 clearance over this, it is no more PZ, but it is addition of delta PZ. It is not because of cutting, but because of the friction. And as this tangential force in the direction of velocity keeps on increasing, you have also the normal force. Usually this normal force from this side, in general we call it Pxy. That means the radial component of the, it is the thrust force. Phi is 90, that is a special case, but phi can be anything between 0 and 90. So, let us put this Pxy as the thrust force exerted on the cutting edge from that side. But because of this appearance of the land, we have to also add delta Pxy, and we can see that this delta Pz is nothing but the friction force addition because of the wear land appearance. Similarly, this delta Pxy is nothing but one n dash, that means you have n dash as this one, and you have f dash which takes this component. So, appearance of n dash and f dash, that happens because of this wear on the cutting tool, and more the growth of this VB, more will be n dash and f dash, that will keep on rising. What are those consequences? One thing, in the very first slide, those was drawn, we have seen that this is the radial loss. So, when it is, this was the material, and when you have this radial loss, that means this one is out. So, this delta R, that means immediately our conclusion is your depth of cut will be less by delta R, and when it is less by delta R, you cannot expect to hold the same tolerance, and if it is a very tight tolerance, then you have to pay that attention whether even if you can go to 300 micron, particularly at the tip of the tool. That means, at the tip of the tool, the wear directly affects the accuracy on the job, which affects the dimension, depth of cut change. In certain case, of course, we have tool wear compensation for advancing the tool, but that also has certain limit. And what is the other limit? Other limit is that power keeps on increasing, that is one thing. And then because of the addition of this Pz, one thing we should also take a note of, that if this is the cutting tool which is supported, it is a cantilever like thing, and here this is the reaction force Pz. Pz tool is exerting force, it is also receiving it is also at the receiving end, and that is the reaction, and as a result of reaction this overhang, there is a chance of this deflection of the tip of the tool. Of course, this depends upon the amount of this overhang and the section modulus. Whatever may be the case, but the fact remains there that there will be little deflection, and with add on this delta z, the thing is not at all favorable, but this is going in the unfavorable direction. So, for these two counts we must pay attention to this tool wear, and if the tool worn area is rough, it is having a direct contact with the job. So, finished surface will be spoiled. That finished surface we have drawn here, finished surface, this one too also finished surface. I can show you that this is the wear on the auxiliary side, this you can see, this is also the wear. So, this wear and the tip wear causes dimensional deviation, and this side wear, that if it is a rough surface, then your surface finish will be severely affected. So, when we sum up these reasons, make a summary, we come to conclusion that why tool wear should be minimized, or we have to pay that attention, great attention to the tool wear, and there are various ways of controlling the tool wear. So, this is something what we can say concerning the tool wear on the flank side, both principal flank and auxiliary flank. Now, come to the cratering. Now, in cratering, this cavity formation does not affect that accuracy or quality of the job directly. What happens? The chip which would otherwise flow smoothly in case of steady cutting, that will go through this groove, and there is a chip breaking action. When it is a very long chip, that helps in breaking the chip, but this is an obstacle in the free flow of the chip. So, force may keep on increasing, that is a fact. However, that is not that critical or risky on the quality of the job. However, what could be crucial and critical, that this cavity, this all on a sudden this cavity does not appear. This cavity appear, say if we take one more sketch, the thing will be clear. Say this is the cutting tool like this. So, more or less it is the cutting action of the work of the tool, and here you have the cavity. It is an, suppose it is an orthogonal. So, chip is flowing in this direction. So, if I take a cross section and I put it on this side, say for example, then what I have? I have the flank wear. So, flank wear part we have to show here. So, this was the thing. So, this is now the flank wear, it is worn out, and this is the land and this is the tool. So, that will be the cross section, and it starts here and it grows. It grows in width on both the dimension, and it depends. So, it is the depth is increasing, width is increasing. Now, when this width keeps on increasing, the crater has two edges, two frontier. One is the trailing edge, another is the leading edge. Now, this leading edge can advance at a faster rate depending upon the wear resistance of this material, and if it come very close to this one, that may be very crucial, because the normal force exerted by the chip, that cannot be any more borne by the small land available. So, because of this radial action of this force, there can be a tearing. So, friend, there also we have to be very careful that how far we can allow this crater to grow, in order that not to promote this catastrophic failure because of this thinning of the section and the land or the material available between the cutting edge and the leading edge of the crater. So, this is the point one has to look in. Now, in most of the cases it is the flank wear which decides the life of the tool, and it is not the case where this crater wear dominates, except where the wear is by some temperature sensitive temperature sensitive wear which is chemical reaction or chemical dissolution. Here one point one has to record. Under any given set of condition I mean one given tool, material, geometry are all set, you have one parametric combination that is also set, everything set, then if you measure the temperature or if you assess the temperature, you shall always find that crater temperature is always higher than the flank temperature. However, on the flank side the contact is rigid between the tool and the workpiece, because workpiece is rigid, but flank temperature is low. But on the other side, when it is chip tool contact, it is not that rigid, because the chip is like a cantilever. When it is a flowing chip, it is only held on this side and it is rigid. That means, so maybe this is one tool and this is the crater, and here we have, this is your chip which is flowing. Okay. So, here the contact is flexible because it is like a cantilever, you have a fixed end, but this contact is rigid. Temperature is high, contact is less rigid, temperature is low, contact is rigid. So, here mostly the under normal condition with the chosen speed, the nature of wear would be mostly abrasive in nature. But here since the temperature is high, why it is high? Because the chip, this material goes through primary shear zone followed by the secondary shear zone, it attains addition of temperature, it is a twofold rise of temperature, and this temperature causes here wear which is known as temperature sensitive, and this wear is temperature insensitive. So, chances of all sort of chemically aggravated, chemically promoted wear will be high, and of course, one thing we assume that in this case the chip is a continuous one, a ductile material, and you have large concentration gradient between the two material, the material on two sides, which promotes the transportation of material from this side to this side, large concentration, absolutely no contents of that material. So, high concentration gradient, then chemical affinity, temperature, pressure, which promotes all kind of dissolution or reaction. These two mechanisms are not same, whatever may be. Finally, one has to look that how much material loss has taken place on this side. So, it is mostly temperature sensitive, temperature dominating, and this side it is mostly mechanical. But it has been found that if we go to very high speed machining with this ductile material with this tool, then also temperature can go to that threshold point where the wear phenomena is no more a mechanically dominated, but it is also chemical in nature. So, that temperature, what is the expected temperature, that one has to ascertain, one has to make a fair estimate or calculation or measurement, and then only we can predict that what kind of tool material or what kind of coating material we can put on that side to combat the wear, and that active surface of the tool, whether it is face or flank of the tool, that is more resistant to such kind of chemical nature of wear. So, friend, I thought this will be very, very useful and relevant, and that is why I touched upon these points. Now, perhaps we can look into the time available, we can look into some of the question or clarification what you ask for. I can look into this. Which type of tool is suitable for tungsten carbide? If you feel it is the machining of tungsten carbide, it should be a diamond tool. Of course, tungsten carbide means whether normally it is not the machining, normally we grind it. Of course, tungsten carbide may be in the green state or tungsten carbide after sintering. So, whether it is a sintered tungsten carbide or the it is a basically it is a powder metallurgy product. So, in that case if it is a green state, definitely diamond which is harder, tungsten carbide is not going to make any kind of chemical wear. So, if it is so, then it can be machined by diamond. But again to tell you, the tungsten carbide, when tungsten carbide itself is a cutting tool. So, this needs shaping and sizing. So, when these issues come in picture, then one has to go for making that shape. Suppose it is a square shaped or maybe in the form of a shaft. Why not? It is not only shape, you can have like cylindrical piece of tungsten carbide, and many structural use also tungsten carbide can be used, not only just for cutting tool, and in that case it is mostly done by grinding and then lapping honing. That is the thing. Why crater is formed of round shape? Friend, very interesting thing and interest question. Friend, to answer this question, I like to just draw your attention here. If you look what I am trying to show, the chip is flowing like that. So, there is a contact, but it is not necessary to contact every point uniform. So, if you look into some of those original research work, you can find the temperature profile is not same. It is actually following the temperature profile and the pressure at each points. So, it is the temperature profile from all the sides and then you have the pressure at all the sides. When you combine this, mostly it is dominated by temperature, you have differential rate of material where from different points. So, and another interesting thing perhaps I can share with you, I do not know, last day perhaps I have told you, let me examine that if you consider the rise of temperature, I think I have touched upon this point and say this is your contact chip tool contact length, chip tool contact length. Okay. So, from this point chip gets lifted. So, this part you have this one, chip gets lifted and this is the shear plane. So, this is, so from this point what happens, though it is the cutting edge, but temperature is not the highest here, temperature is highest at a point behind. It is the simple reason that this temperature, that heat is conducted away by this workpiece. So, temperature is high. That is why you can also see that depth, crater embryo, nucleation of this crater or embryo formation, whatever way you like to say, that starts from a point I mean just behind the behind the cutting edge. It is not on the cutting edge and gradually it spreads on both the sides. And friend, this is the reason the temperature profile not only along the direction of chip flow, but also in this direction. These two combination makes this kind of profile. Okay, friend. Thing is that I would say one is the cause and another is the effect. It is not diffusion, I would say basically you have temperature sensitive. When you take the cutting phenomena in the temperature sensitive zone, again I repeat that it depends upon the selection of these two. I am concentrating only our discussion on the chip side because the temperature is higher than on the flank. So, friend, here you have certain level of temperature, it depends upon so many things, thermal conductivity, volume specific heat, energy consumed, friction and so on. So, when you finally attain certain temperature and at that temperature you have to really see the reaction between the work material and tool material or the mutual solubility, and it would be interesting if you look into any fundamental book on chemistry or material science, what is meant by solubility, when those two materials becomes mutually soluble and have their solubility, and when they are having reactivity. So, the reason of reaction and reason of dissolution may not be the same. Whatever may be the thing, when it is dissolution or reaction, finally it will be transportation of the material, and there that we refer to as diffusion. One thing very interesting I must share with you, that when we have this chemical reaction or dissolution, one layer gets removed. When it is a reaction layer or a dissolved layer, you have a reaction product, and that reaction product from on the tool surface, that does not have the same property as of the parent material. Say I can give you very specific example. This is the chip. Okay. Now, this is tungsten carbide plus cobalt, and this is your low carbon steel, say C20 steel, and you are machining with a speed which promotes such thing. So, you can understand this is a 0.2% carbon. So, what will happen at that temperature, if you take the whole thing to that temperature, that will promotes dissociation of tungsten and carbide to tungsten and carbon. It will dissociate. Then this carbon will migrate to this side. Why? Because of the simple reason, it is a low concentration of carbon and it is a high concentration of carbon. And when such thing happens, you have a layer which we call deficient in carbon. Then iron comes from this side, and what we have one called, it is Fe2W2C. It is a solid solution of iron, tungsten. It is solid solution of tungsten carbon into iron. Iron goes in this side, comes on this side, and then it makes this kind of thing. It is called a complex carbide solid solution, and carbon goes on that side. It is a dark layer which is rich in carbon. That means mild steel get enriched at this point because of the migration, and iron comes in, and beneath that what we have. So, you have a layer which is a part of the chip which is rich in carbon, but you have a layer just on the surface, top surface, which is in the form Fe2W2C, and beneath that what we call have a phase what we call Wx COY and CZ, that we call eta phase. It is deficient in carbon. So, friend, originally if you look back, originally it was C20 steel and it was rubbing, under the action of rubbing over tungsten carbide cobalt cutting tool material. But because of this dissolution and diffusion, you have enrichment of the layer of this chip which is in contact, and it becomes enriched with carbon, it flows, and then on the top surface of the tool it is no more tungsten carbide, it is now this layer. So, property of this layer, this surface which is the tool material, and this one, these are not same. So, this is less in inferior in property, and this one another eta phase which is a hard and brittle, very brittle and porous, it is just below. So, first of all you have this layer on the tool, and beneath that you have this layer which is called decarburized layer, deficient in carbon. Now, once that is formed, you have abrasion is also there. So, since this material cannot possess the same wear resistance like tungsten carbide, this will be simply abraded, and this is called post diffusional. So, that means it is after diffusional. post diffusional abrasive wear. That means, from this post diffusional abrasive wear, that means we have a migration of the material, dissolution, or it can be chemical reaction in some other cases, and as a result of that we can say in a sentence or two there is a structural change on the working surface of the rake, and this is no more tungsten carbide and cobalt. Cobalt is the matrix and tungsten carbide which offers the wear resistance. It is no more tungsten carbide and cobalt this composite, rather it is this one and this is supported by this one, but this is a porous structure number 1, it is brittle and hard. So, all this thing it cannot bear that load. So, it is also literally it is washed away by this flowing chip, it is abrasive action. So, friend, this is one very interesting example what happens when we use this kind of tungsten carbide cobalt, which is not at all recommended, but if one like to see and experiment himself with such kind of combination, what is mean by this thermally sensitive wear, he can immediately get that experience, and we say that this is the diffusion is the cause and then this is the effect. So, it is first diffusion followed by post diffusional abrasive wear which takes place at a faster rate. So, once this is washed away, you have again appearance of tungsten carbide cobalt on the rake, and again you have change of this structure, again that is washed away, again you have. So, process keeps on repeats itself. So, it is not just diffusion, I would say it is the effect of diffusion and post diffusional abrasive wear that actually causes that rapid wear.
When coolant is used, what is the percentage of tool life improvement?
Is the percentage
of tool life improvement when coolant is used?
Tool life?
What is when coolant is used? What is the percentage of tool life improvement?
Tool life improvement, because of what, that also you have to say. Tool life improvement, to make some improvement you have to change coolant. Okay, friend.
What is the percentage of tool life improvement?
Okay, friend, it depends upon so many factors. First of all, what speed you are working, okay, and then another issue is that how much temperature drop you can have. It is not the effect of coolant, how much efficient it is in bringing down the temperature, because wear is now in the temperature sensitive zone. So, you have to look into how much will be the drop in temperature because of this application of coolant. Now, there are two types of coolant, one is at the interface between the chip and the rake, or if space which is between, say here, I hope you can see this thing, this place. So, this place, that means this is the flank. So, if you have something, a way of applying the coolant, in that case you have some kind of drop in temperature. So, if you see that temperature sensitiveness of this wear, if it is understandable, then you have to look in by the application of coolant how much is the drop in temperature. So, if you can have sizable drop in temperature, definitely that will help you. If it is well beyond the reactivity or solubility zone, definitely you have an improvement. Friend, what are those major factors? Now, these factors come from which side, that is important. Which say it can be a tool wear. You can also reduce the wear on the tool by special formulation of the cutting tool. I amend my statement. So, you can reduce the wear on the tool simply by formulation of the workpiece without much affecting its basic property, because tool this work material is meant for making some components which are going to be used for making some machine or building some structure. So, here the important thing is that there are certain ingredients during this chip formation, those materials gets stuck to this tool surface. That means, what I mean to say here, say this is the cutting tool, and this is the uncut layer thickness. Okay. So, this is the interface, that is your point of attraction or attention. So, here if you have certain material and which can come and make say layer here, and in that case that layer prevents direct contact of the chip with the tool, that layer keeps on forming as the chip keeps on flowing, and in that case that layer with a material which comes from the workpiece side, that protects the tool. I can give you one specific example of aluminum deoxidized steel. You know, aluminum, titanium or calcium, these are used for deoxidation of the steel, and if this aluminum is used, and it has been established in research that this aluminum can come over here and it can put a layer of aluminum oxide, and this aluminum oxide layer can also prevent this crater wear sizably. So, this way also your work material can be a factor which prevents this wear on the cutting tool. Then comes the geometry of the tool. So, geometry of the tool, friend, on one side the geometry is responsible for increasing the force or decreasing the force. Now, you have to make a decisive action that this increase of or decrease of force will lead to certain heat flux. Now, this heat flux will cause rise of temperature depending upon the mass available at the tip of the tool. So, when this energy is low, but your material available at the tip of the tool is lower than that, then definitely that makes no benefit, rather it will lead to rise of temperature. Now, on the other side, if you have more mass, means you have to put less clearance, you have to put negative brake, and if that should be the case, you have more mass, means temperature rise will be less because of this MST, mass specific heat, and delta T, rise of temperature. But in that case your energy requirement will be high because of the simple reason that negative brake means large value of the force, low clearance angle means you invite or promote rubbing, that will be also direction of velocity. So, that will also lead to rise of temperature. So, ultimately it is the energy required or the power required for cutting action, and then the mass of material which is available around this tip of the tool. So, higher the mass, less will be the rise of temperature, but at the same time this large quantity of mass accumulation because of choice of low clearance angle and negative brake, you have to also look that should not become also counterproductive. So, this is another way to look into. And then coming to your this coolant, that also affect your tool wear. However, friend, here is the thing that whether you are doing flat cooling or jet cooling to really target that source of heat. So, there are now various techniques, chip tool interface, just by putting a nozzle from this side. This nozzle, the way conventionally we do, it won't give you much of the benefit because it cannot penetrate, because this pressure is quite high. So, you have to this pressure should be exceeding that one. So, there are ways so to direct the nozzle from, you have the some perforations like nozzle from this side you can apply over this, or from this side. So, it is the temperature interface which you can cool, or you can cool the work flank interface. If you try to cool, that also give you the benefit on this side, in that because heat will be conducted. So, if you lower this temperature, definitely your flank temperature will also come down. And I have already mentioned that in most of the cases it is the wear on the flank that limits the life of the tool. So, even if you have some benefit here at the chip tool interface, that indirectly helps in elevating the life of the tool or reducing the wear on the tool. So, it is bulk cooling. Bulk cooling may help your workpiece, but bulk cooling as such may not help in getting the retardation of the wear, because it is the concentration where the wear is taking place, that particular place need to be targeted to have immediate and rapid action of cooling and immediate benefit. No, if you can model the process, if you can profile accurately, you can get the accurate profile. There is no problem. You can measure this crater profile by a telesub or a non-contact along the direction of chip flow and normal to the chip flow, and there are models available in many of the advanced books, by which you can accurately predict the profile of the crater if you know the temperature profile and this what we call mass transfer by this diffusion process. This profile can be with fair accuracy, it can be predicted, and those things has been already done. So, it is not to suggest that this is just an not predictive or inaccurate, what perhaps you mean inaccurate. It is nothing like that. There are models and accurate, there are models which are all documented in any leading textbook, and you can go through that. Those things are available, but those are mostly meant for M.Tech students, and but if one is interested and if he has an interest to go deeper into the subject, he can definitely do that, and I strongly recommend you go through those chapters and sections dealing with tool wear and predictive model of crater. This is already available. Okay, friend, it is not the rust, it is not the question, it is the rough surface. You see, it is clear when the job you receive from a foundry shop or from a forging plant or from a rolling plant, you have, if it is hot working, then you have an oxide layer on that surface which is strain hardened and which is already having a different luster character, not just like the core area where you get a metallic luster. Now, if it is hard and sharp, if the hardness is changed, when it is strain hardened, hardness goes up and it is like an oxide scale. If that is the thing, at that point the wear will be quite high, but when you remove that one, definitely the soft area your wear will be less. So, it is not the question of rust, rather it is the question of that mechanical property, that hardness, unevenness, mostly it is the hardness that comes in picture. With that, I thank you so much for being with me, and I wish all the best, particularly concerning this subject. And having said that, I wish that you take interest in that subject and have the pleasure and doing some in-depth study in this particular subject. Very interesting, very important, not for our growth, but for the growth of this machine tool and machining industry.